Hello, this is Dr. Amudapriya, Associate Professor, Tripoli of Rockney College of Engineering and Technology, Palkulam. We are discussing about the subject protection and switchgear. Let us now discuss about the transformer protection. Earlier we have seen about apparatus protection, and transformer, when considering, is a vital part in the power system because the voltage value completely depends upon the transformer operation. The power transformer has the most important links in the power transmission lines, I mean the distribution system. It's a highly reliable piece of equipment, and this reliability depends upon adequate design, careful erection, proper maintenance, and application of protection systems. The protection equipment includes surge diverters, gas relay, electrical relays, and there are very large transformers which has to be provided with the best protection. Normal types of faults which are occurring are overload faults and the external short circuit faults. A transformer must be disconnected when such faults occurs only after allowing the predetermined time during which the protective gears should have operated. While considering the internal faults like a LG fault, LL fault, LLG fault, LLL faults, interturn faults, and earth fault, so-called incipient faults, which are initially the minor faults, etc. And the nature and effect of transformer faults are source and earthing impedance. A fault on transformer winding is controlled in magnitude by source and neutral earthing impedance, leakage reactance of the transformer, and the position of the fault on the winding. So while considering the earth fault on resistance, earth star winding, we can see this diagram here. Left hand side there is a star winding, and right hand side there is a star winding. The transformer differential protection, it is mainly related to Merz price scheme, and hence there are certain limitations. Right, the repetitions cannot be omitted, etc. The nominal currents in the primary and the secondary sides of the transformer vary in inverse ratio to the corresponding voltages. This should be compensated for by using the different transmission ratios for the CTs on the primary and secondary sides of the transformer. While considering the current transformer connections, when a transformer is connected in star or delta, the secondary current has a phase shift of 300 degree relative to the primary. This phase shift can be offset by suitable secondary CT connections. Negative sequence currents which are flowing through the star side of the transformer will not produce the current outside the delta on the other side. The zero sequence current must therefore be eliminated from the star side by connecting the CTs in delta. The delta on the delta side, it should be connected in star in order to give 300 phase shift. When the CTs are connected in delta, their secondary ratings must be reduced by 1 by 3 times the secondary ratings of the star connected transformer in order that the currents outside the delta may balance with the secondary currents of the star connected CTs. If the transformers are connected in star, the CTs on both the sides would need to be connected in delta. Suppose if the transformer has a benefit tap changer, it is possible to vary transformation ratio for voltage control. The differential protection scheme should be able to cope up with this variation. So this is because if the CTs are chosen to balance for the mean ratio of the power transformer, a variation in ratio from the mean will create an unbalanced proportional to the ratio change. At maximum through fault current, the spill out produced by the small percentage of unbalance may be substantial, and the differential protection should be provided with the proportional bias of an amount which exceeds in the effect the maximum ratio deviation. This stabilizes the protection under true fault conditions while still permitting the system to have a basic sensitivity. When we consider the magnetization in Russia, this produces a current flow in the primary winding that does not have any equivalent in the secondary winding. The net effect is whenever there is an internal fault of the transformer, the effect will be considered. Since the differential relay sees the magnetizing current as an internal fault, it is necessary to have some method of distinguish between the magnetizing current and the fault current. Using a differential relay with a suitable sensitivity, with the sensitivity to the magnetizing current usually obtained by a unit. It introduces a time delay to cover the period of initial inrush peak. Using a harmonic restraint unit or supervisory unit in conjunction with the differential unit, inhibiting the differential relay through energizing the transformer. So we can see this diagram. We can have a definite case. So we do have CTs at each phases, and then we do have the transformers at each phases where the differential protection is being considered. Compared to the differential protection in the generator, there are certain important points actually in this case of transformers. Here we do have the coil which are connected in 3 phases, and we do have it in OPs. So in case of power transformers, the phase difference between the voltages induced in high voltage winding and low voltage winding, there is a complete phase difference. Next one is the Buchholz relay. Actually, Buchholz relay is a container. You can see it is all falls below the oil in transformer results in the dislocation of the breakdown of oil. Some degree of arcing will always takes place there. The resulting composition of it will release gases like hydrogen, carbon monoxide and hydrocarbons. When the fault is of very minor type, then such hot joint gas released slowly, but a major fault involving severe acting causes rapid release of large volumes of gas as well as oil vapor. Such incipient falls of smaller or large magnitudes can be detected by a gas actuator relay known as Buchholz relay. The Buchholz relay is contained in a cast housing which is connected between the conservator tank and the main tank of the transformer. And this is Buchholz relay. Here we do have the fixed contact and moving contact. This is an alarm circuit is connected. Here this is connected to a trip circuit. Obviously the same thing. Here we do have transformer oil intake, and that is out. When under normal condition, the springs will be intact and it will not be getting attracted towards the electromagnetic plate or fall valve, etc. whatever it is. But during fault conditions, the coil, it gets connected to the trip circuit. This flap valve will move towards this trip circuit. This will be activated to the trip circuit, and the trip circuit will be opening. Before that, this activation is also being, the float tilting is also being closed to the alarm circuit, and an alarm exhibits its force. There are certain limitations where only for oil immersed transformers we can use this, for not for others, and for falls below oil level are being detected. And the relay is a slow one which is operating for a minimum operating time of 0.1 seconds and an average time of 0.2 seconds, but it has many more applications. Thank you.